This conference will now be recorded.
Hello everyone. We ended at this slide, which is formal charge, but still there is some we have to know about this formal charge. Okay, so we'll start with the next one. So we have seen how to calculate this formal charge with the formula, but sometimes more than one structure will be there. So what is the base representation that we have to know? So today we'll discuss formal charge and then exception to the octet rule and problem related to that, then ionic bond or electrovalent bond, and we'll also compare ionic bond with covalent bond. So formal charge, we know how to do the calculation, and after calculating that formal charge, the base representation of Lewis structure, how to choose. So for that we just have to keep these points in mind. So the structure in which all the formal charges, they are zero, that will be preferred over the one where there is some charges present. So just have a look in the previous slide that we have finished in the last class. There are two structures possible for carbon dioxide, but we have discarded the second one. This is actually correct one because here the formal charges are less compared to the second structure. So that is actually this first point that is mentioned here, a structure in which all formal charges are zero, that is obviously preferred over the one where you have some charges. And suppose in one structure there is small formal charge, in another structure there is high formal charge, that is -1 over oxygen in one or -2 in other. So obviously you should prefer the small formal charges. So as zero is preferred, so obviously after zero, if you cannot avoid charge, you have to put charge, then obviously between small charge and high charge, small one will be preferred. And when there is both negative charge, that is not both, I am trying to say, suppose two possibilities are there where you can put the negative charge. So you have to just compare which one is more electronegative. So more electronegative atom, you should place this negative formal charge, and vice versa. That is, if it is positive formal charge, that should be placed on the more electropositive atom. Okay, so these are some of the points that we have to keep in mind. But though it is true that the last point is saying negative charge should be on most electronegative, but in some cases you may see that there is positive charge over oxygen or fluorine, but still that structure is accepted. So don't be surprised, because there is some other factors that we have to give more significance, and that factor is if octet is complete in that structure, even if it is carrying some positive charge over oxygen or fluorine, it's fine. You just have to give more preference to the fact that octet should be complete, even if oxygen is carrying positive charge or fluorine is carrying positive charge, it's fine. A few more points to keep in mind. Formal charges, they are basically theoretical charge. So don't think they are actually the real charge separation. Just take any molecule, there is some, when you have calculated the formal charge by applying the formula V minus N minus B by 2. So suppose you have applied this formula, you are getting some charge. So don't think that they are actual charge. They are just, so that is why the term is formal. Okay, it is theoretical. So they do not indicate real charge separation within the molecule. Formal charges help in selection of the lowest energy structure from a number of possible Lewis structure for a given species. So just take the example of carbon dioxide that we have seen in the last class. In one structure we are giving more preference, so that is obviously the less energy structure, and less energy structures are always preferred. Then generally the lowest energy structure is the one with the smallest formal charge, and you will always see that lowest energy structure, you will see it is always associated with the smallest formal charge, and that is why in the previous box we have mentioned that the second point, just focus on this second point, A structure with small formal charge is preferred. So it is actually, why it is preferred? Because it is associated with less energy, and less energy is always preferred over high energy, because a system always tries to be stable as much as possible. The formal charge concept is based on pure covalent view of bonding. Now, covalent view of bonding means, so there is bond between A and B, these two atoms. And there are two electrons present that is shared between them. So that is the covalent view. Here we are not considering any fact that is based on ionic bonding or electrovalent bond. That is, one atom has completely given electron, another one is completely accepting. We have not considered any of these things. We have purely considered covalent view. Okay, so formal charge, this concept based on covalent bond formation view, not ionic, where the electrons are shared equally by the neighboring atoms. Okay, so here we will solve two problems. What is the formal charge on carbon atom present in the following two structure? So what type of structure we have? The first molecule is carbon disulfide. You know what is carbon dioxide, CO2, right? So just in place of oxygen, if we have sulfur, that molecule, just analog of carbon dioxide, that molecule is CH2. And you can see there is similarity in structure with carbon dioxide, right? So double bond with two sulfur both side. So we have to calculate formal charge for carbon only. And the second structure is basically polyatomic ion. More than one atoms carrying two negative charge overall. So this is polyatomic ion. One is neutral molecule CH2 carbon disulfide, and the second one is polyatomic ions, which is basically carbonate ion CO3 carrying two negative charge. Okay, and this molecule is CH2. Now for the first one, carbon, we will use the formula. Remember, total valence electron for carbon, it is 4. Then after 4, minus non-bonding electron. Now carbon has used all its 4 valence electron in the bond formation, total 4 bond formation. All the electrons are used up. There is no non-bonding electrons over carbon. So this is 0. Then B by 2, where total number of bonding electrons. Now rather total bonds are actually 4 surrounding carbon. So obviously number of bonding electrons 8, and 8 by 2 is 4. So rather than considering B by 2, I will suggest just count how many how many bonds are there. So it is 4 bonds. 4 bonds means 8 electrons, and 8 by 2 is 4. So directly take 4 bonds. So it is 4. So what you are getting? You are getting 0. So for the first one, it is 0. So these two not possible. Come to the second one. Here also carbon is having total 4 bonds. So all these 4 valence electrons are used up, no non-bonding electrons, right? And same type of situation. Here also it is. So that is why correct option will be the second option. Fine. Here we have a molecule which is basically ozone, O3. Okay. Formal charge of oxygen labeled 3, 2, 1. So there are total 3 oxygen. Number 2, number 1, number 3. 3 different numbers are given, because if numbers are not given, all are same atoms. So that is why it is better to put number 3 to 1 in this molecule, and we have to find the charge. So if you look at the options, the first value is for 3 number oxygen, then 2, then 1. So this is for 3, 2 and 1, because respectively 3 to 1 in ozone respectively. So for oxygen number 3, If you look at oxygen number 3, only one bond. That means out of 4 valence electron, oxygen is using only one valence electron here, right? So all these are non-bonding electrons, 1, 2, 3, that is 3 lone pairs you can see. Then if you look at oxygen number 2, here 2 bonds. So oxygen is using only 2 electrons in these 2 bonds. And out of 6 valence electrons, 2 used in bond formation, rest of the 4 are present as non-bonding in the form of 2 lone pair. Come to the middle oxygen. Middle oxygen total 3 bonds. That means out of 6, it is using 3 electrons in these 3 bonds. Fine. Now see the calculation. For number 3, because it is first, so let's see it first. It is 6. Because valence electron, it will always be 6. There is no doubt in that. And then number of non-bonding electrons, total 6, that you can see in the picture. And total number of bonds is only 1. And 1 bond means 2 electrons. So 2 electrons divided by 2. So in this calculation, you are getting the charge -1. Then come to the other terminal oxygen, number 2. Now total number of non-bonding electrons 4, which you can see in the form of 2 lone pair. Total number of bonds 2, that means total bond electrons in bond formation involved 4. So 4 by 2, that is 2. So you are getting 0. And the middle oxygen, which is number 1 oxygen. Here non-bonding electrons left only 2. And total number of bonds 3. That means 6 electrons. So 6 by 2. So that is why here charge is +1. Okay. So it is +1. So 0, then +1, then -1. But remember, you have to follow these respectively. 3 first, then 2, then 1. And 3 is -1. Then number 2 oxygen is 0. This is +1. So this you can find in option 3. Okay. Exception to the octet rule. So there are some octet rule we have seen, but when you can get some exception, that also we have to know. It is not applicable for all the elements. It is exclusive for non-metals, and not just any non-metals. It is the non-metals only for second row of the periodic table that is applicable. So oxygen, nitrogen, carbon, you will see octet rule is always it is successfully you can apply it. But there are some cases where you can find exception and octet rule is not maintained. So what are those cases? The first case is molecules with odd electrons. So there are some molecules where total number of electrons are not even. It is 7 or 11 like this. We will obviously see example. And the second situation arises when there is incomplete octet of the central atom. That means surrounding the central atom, total number of electrons present is lesser than 8. So that is why it is incomplete octet. And the third case, which is reverse of the previous one, expanded. That means now surrounding the central atom, total number of electrons involved is greater than 8. So that is why we are calling it expanded. Okay. So these are the 3 situations where you can see some exception to the octet rule. Now, why only second row elements are giving us successfully, that is why they are obeying this octet rule always, why it is not maintained by other rows? The reason is second row elements, if you see, they have only s and p orbitals. There is no d orbital possible. Have you ever heard of 2d? No. The first d orbital starts 3d, 4d, 5d, but not 2d. But in second row, maximum you can have 2s and 2p. Now in 2s and 2p, maximum number of electrons you can accommodate 8. That means they cannot exceed octet. Okay, so this is the reason. Now one by one we'll see all the situations. The first situation, molecule with odd electrons. Few molecules have a central atom with an odd number of valence electrons. Now directly there is odd number of valence electrons. So that is why when you count the total number of electrons, that will also give you odd electrons. So two very important example or very common example whenever we discuss this exception of octet rule with molecules of odd electron, very common example is NO2 and NO. We know there are different types of oxides of nitrogen. NO2, NO, N2O, N2O5. Okay, and these two we have chosen here because they are having some odd electron. Total number of electron odd, because see, for nitrogen it is 7, right? And for oxygen we know it is 6. So 6 into 2, 12. So 12 plus 7, 19. So overall also obviously it will be odd. Then NO 7 plus 6, total number of electron 30. That is also odd. So in this case, octet configuration we will not get. So nitric oxide molecule, nitrogen out of 5 valence electron, 2 electrons used here. These two are present as lone pair or non-bonding. And this is also non-bonding, but you cannot call it lone pair because it is not pair. It is a lone electron. Lone means single electron. So this is actually the odd electron. Okay. And if you look at the other side, from oxygen point of view, out of 6, 2 used with bond formation with nitrogen, and the other 4 electrons remaining as 2 lone pair. So with respect to oxygen, octet is fulfilled, because if you focus on oxygen, surrounding oxygen, total number of electrons 8, 4 electrons in 2 bonds, then 4 more, so it is 8. But if you consider from the point of view of nitrogen, surrounding nitrogen, how many electrons? Total 4 in bond and 3 as non-bonding. So 3 plus 4, it is 7. So octet is not complete. Okay. NO2. Now both side we have oxygen. Nitrogen, it is using 2 electrons here. Then nitrogen, this bond is actually coordinate bond, and this bond is shown like this. While nitrogen is using both the electrons, that is normally what we know, when there is a bond between nitrogen or any other, that is A or B, one electron given by A, another electron given by B. But when there is a coordinate bond, both the electrons are given by a single atom. So in this case also same thing is happening. So this bond is basically coordinate bond because both the electrons are donated by nitrogen. So nitrogen, out of 5 valence electron, 2 used up in the left hand side, 2 electrons completely donated from nitrogen, and this is the single electron left. But if you look at the 2 oxygen, this oxygen, out of 6, 2 used up in bond formation with nitrogen, these 2 are lone pair. So same type of situation as you have seen here. But what about the right hand side oxygen? The right hand side oxygen, out of 6 valence electron, all these 6 valence electrons are present as the 3 lone pair, because in this bond between nitrogen and oxygen, oxygen has not given any electron. Both the electrons are coming from nitrogen. Okay, so that is why this is coordinate bond. Sometimes you will see in books that NO2, it is written in this way, because coordinate bond, which is also known as dative bond, the direction is from nitrogen to oxygen, the electrons are coming, right? That is why the direction of the arrow is towards oxygen, as if both the electrons are coming from nitrogen. So this type of picture also present. But here we are using simple Lewis diagram, so you have to use all the dot sign. But the important point that you have to remember, it is odd electron. So if you consider these 2 oxygen, surrounding oxygen, whether it is right hand side oxygen or left hand side oxygen. In both cases, octet is complete. But if you focus on nitrogen, you will see surrounding nitrogen, total number of electrons 7. So octet is not complete for nitrogen. So that is why it is odd electron molecule. So this is the first case, exception to the octet rule. Second case, incomplete octet of the central atom. In the previous case also incomplete octet for the central atom, though for nitric oxide directly we cannot use its central because there is only 2 atoms, N and O. So what are the examples? Mainly we'll see these examples are from beryllium, aluminium and boron. Here the number of electrons surrounding central atom is lesser than 8. So species with incomplete octets, they are rare. Only for these elements you can find these examples. You can see the molecules BeH2, beryllium hydride, aluminium chloride and BF3. Now Be, which is from, this is group 2 element, alkaline earth metal, the first element. If you consider row wise, it is the second period. The first element lithium, group 1, second element, the next after lithium, beryllium. So group 2, that means general electronic configuration is NS2. It is second row, so it is basically 2s2 and atomic number is 4, so 1s2, 2s2, total 4 electrons. So out of these 2 valence electron, both are used up in the bond formation with hydrogen. So this is one bond, this is another bond, but surrounding beryllium, how many electrons are present? Total number of electrons 4. So octet is not complete. Okay. Next example, BF3. Boron, it is from group 13. Now for group 13, the general electronic configuration is NH2 NP1 and boron is from second period, so it is 2s2 2p1. So total number of valence electron only 3. Now out of these 3 valence electron, all these 3 electrons are used up in the bond formation, covalent bond formation with fluorine, right? And if you, so this is for the central atom, but if you consider from point of view of fluorine, fluorine has total 7 valence electron because it has configuration 2s2 2p5, and out of these 7 valence electron, 6 are present as lone pair, total 3 lone pairs surrounding fluorine, and 1 electron is using for bond formation with boron. So surrounding boron, how many total electrons? 3 red, which is its own, 3 blue, which is coming from 3 fluorine atoms. So total electrons 6, which is lesser than 8. So that is what is exception. Now you can see some more pictures in the right hand side. Okay. So what it means? So see, what is the difference here? And why we have drawn these pictures? That is the question. So actual structure is this, but we are having some more resonance structures, and that is because here to avoid this that is incompleteness of octet, because boron is electron deficient, octet is not complete. What maximum this molecule can do, any of this fluorine, it can donate one of its lone pair to boron. Now when it is donating, after donation there is a double bond, so there will be negative charge over boron, though you cannot see any negative charge here. That is fine, you will see after some time. So there is a double bond, and one of the lone pair over fluorine is now less, only 2. Rest of the fluorine it is 5, just as before, 3. So this is one possibility. The second possibility is, suppose this is fluorine number 1, this is fluorine number 2, this is fluorine number 3. So it is for fluorine number 1. For fluorine number 2, now it has donated. So now lone pair reduced from 3 to 2, and the double bond is between fluorine number 2 and boron. And the last possibility. So when you have this type of structure, Now if you focus on boron, you will see total number of electrons surrounding boron. Now it is 8. So just to fulfill this electron deficiency, that is incompleteness, incomplete octet of boron, fluorine can donate electron. And when it is donating electron, after donation, there is negative charge over boron, that is a formal charge, and positive charge over fluorine. And that will be like this. Let me clear all this. So now look at this. So this picture is with formal charge. You can calculate the formal charge. You will get this value of +1 or -1. So just use the same formula we have used some time ago. That is V minus N minus B by 2. If you use that formula, you will see the fluorine which has donated electron, there will be a positive charge. And each time boron is accepting, so there will be negative charge. But it is formal charge. Okay. So these are the resonance structures, because only after this type of resonance octet is complete. Now you can say that fluorine is the most electronegative element, how it can carry negative positive charge. But remember, one point I have mentioned one slides before, that even in some structure you are getting positive charge for fluorine or sometimes for oxygen also. So don't be surprised, because only by doing so the electron deficiency of boron can be removed. So that is why, though there is positive charge, but still these type of resonance structures are possible. Okay. Now, what is the evidence? So these structures is supported by the fact that experimentally determined bond length of boron to fluorine bonds in VF3 is lesser than that would be typical for a single bond. So if it is purely BF single bond, then there is a bond length value. If it is purely BF double bond, then there is a bond length value. Now the bond length of single bond, it is always greater than the bond length of double bond. Now if suppose these resonance structures are not possible, only the first structure is possible. So experimental value, we should get only the single bond experimental value. But experimental value that we are getting, it proves that the bond length is not exactly double bond, it is not exactly single bond. So it is something in between, it is slightly lesser than single bond. So it is not purely B double bond F, it is not purely B single bond F. So it is basically the average of these three structures. If you take, it will be something like this. So single bonds are always there, but this double bond, sometimes it is present between fluorine 1b, sometimes fluorine 2b, sometimes fluorine 3b. So it will be something like this, average structure, negative charge. Okay. So when you consider this average structure, experimental value, it is not purely single, purely double, it's something in between. Okay, so this is the evidence. The third possibility, expanded valence shell. So it is the reverse case of the previous examples that you have seen. So central atom is having lesser than 8 electrons, but now they will have more than 8 electrons. And how it is possible? It is possible only with third row elements, because when you have third row elements, that is phosphorus, sulfur, now 3D is possible. So they can have 3s, 3p, and after that 3D also. Okay, so the paired electrons, you can unpair them and you can shift them to 3D. So more number of unpaired electrons are now possible. So molecules with expanded valence shells, it is more common than incomplete octet. So the previous case, that is actually rare. It is only you will see for boron, aluminium, or beryllium. But this case, compared to the previous case, it is more common. In this case, the central atom in the Lewis structure will be having 8 electrons, more than 8 electrons in its valence shell. So third period elements are basically involved here. They occasionally exceed the octet rule. It is not that mandatory that any third row element they will, in all their molecules, they will expand their valence. No, that is not necessary, but occasionally in some molecules where it is needed, by using their empty d orbitals to accommodate additional electrons. So first we have taken phosphorus, and what molecule? Sorry, what molecule we have taken? It is PCl5. So PCl5 is such an example. Here we have total 5 phosphorus chlorine bond. Now focus on the central atom. It is from group 15, just below nitrogen. Group 15 means valence electron, the last digit 5. Valence electron 5. So these 5 valence electron, you can already see electronic configuration, how they are arranged. It is 3s2, 3p, 3. But if you simply maintain this electronic configuration, maximum you can get 3 unpaired electrons. But you have to make total 5 phosphorus chlorine bonds. So we need 5 unpaired electron. How you can get? So this electron must be shifted here. So this is the ground state configuration, but excited configuration you can write where it will be 3s1, then 3p as it is present, and 3d, one more electron here. So now total 5 unpaired electrons, right? So all these 5 unpaired electrons, now they can form bond with 5 chlorine. And if you are curious about chlorine, it has configuration 3s2 3p5, 7 valence electron. Out of 7, only 1 is used up for a single bond formation with phosphorus. Rest of the 6 electrons present as 3 lone pair. Same for each chlorine. Now if you focus on phosphorus, how many total number of electrons are present? So 5 electrons I have already drawn with black color, and these electrons are coming from 5 individual chlorine atoms. But surrounding phosphorus, how many electrons are there? It is 10 electrons, and 10 means now it is greater than 8. So octet expanded. Fine. One more example is SF6. Now in case of SF6, sulfur, which is from group 16, that means 6, the last digit of 16, that is the valence electrons. So total number of valence electrons are basically 3s2, 3p4, like this. But how many unpaired electrons you are seeing here? Only 2, right? But we need how many unpaired electron? We need total 6 unpaired electron. So that is the reason we have to break these 2 pair in excited state. So this will be shifted here. So after shifting, the electronic configuration will be like this: 3s, 3p, and 3d. So now total number of unpaired electrons 6. Okay, so 6 electrons it will be using for bond formation with 6 fluorine, and each fluorine there will be coming 1 electron. Now surrounding sulfur, now total number of electrons. Basically, I am just drawing all these electrons so that it is clear to you. Even if you do not draw, you can easily understand, as there are total 6 bonds surrounding sulfur. So obviously, total number of electrons will be 12. Even if I do not draw it, it's fine. You can still understand. So 12 electrons, that means it is greater than 8. So it is expanding the octet, okay? So larger is the central atom, higher will be the number of electrons it can that is surround it, and expanded valence shell occur most often when the central atom is bonded to small electronegative atoms. Now see, sulfur is accommodating total 5. Now fluorine, chlorine, they are also having some volume space, right? So individual, if I draw the atoms like this, though they are having some space. So smaller is this space volume, better it is. It can accommodate, that is accommodation will be easier. So that is why it is mentioned in the last point that whenever we have this type of molecules, small electronegative atoms are favored, such as oxygen, chlorine, or fluorine. Okay, so accommodation will be easier, because if these atoms are very large, suppose iodine or bromine, then it will be very large like this, accommodation will be really difficult. So that is why it is preferred for HCl or oxygen. Okay. We have a question here. A student represent the Lewis dot structure of aluminum chloride molecule as shown. The structure is given, but you have to answer that whether this representation is correct or not. That is the first question. And the second question is, if the chlorine atoms here are replaced by bromine atoms, chlorine atoms replaced by bromine atoms, that means now the molecule will be AlBr3. Okay. What will be the number of electrons present in the valence shell of aluminum? We'll obviously come to the first point, first question. Look at the structure carefully. Aluminium is from group 13. Now group 13 means you have to consider this last digit, which is 3. So 3 is its valence electron. It is actually 3s2 3p1. Now 3 valence electron, and if I draw the structure like as if there is 3 bonds. Okay. Now aluminium, it will be using 3 electrons in these 3 bonds. Is there any electron left? No electron left for aluminium. So surrounding aluminium, there should be 6 electrons, because 3 bonds are there, so 6 electrons, and no non-bonding electrons are possible for aluminium because it has total 3 valence electron. All these valence electrons are used up in these 3 bonds. But if you look at the picture here, basically if I draw this for this structure also, chlorine, it is 3s2 3p5, 7 valence electron. Out of these 7, 1 will be used in bond formation, and rest of the 6 will be remaining as 3 lone pair. So that is correctly represented in the structure for all these chlorine. That is fine. And this is the bond between aluminium and chlorine. Okay, so up to this point it is totally fine. But the problem is, this is not possible at all. There is no non-bonding electron. Non-bonding electron is not present. So where from this lone pair is coming over aluminium? Basically, aluminium chloride is an example of incomplete octet. Remember the second case, we have given 3 examples: BH2, AlCl3, BF3. Out of these 2 we have seen, but right now you can see AlCl3 also. AlCl3 over aluminium lone pair is not possible. So that is why, is the representation correct? No, the representation is not correct. Come to the second question. If the formula is AlBr3, is there any change? What will be the number of electrons present in the valence shell of aluminum? Now when it is bromine, what is the difference between chlorine and bromine? Chlorine is 3s2 3p5, but when it is bromine, the next element, it is basically 4s2 4p5. That is the difference. So only principal quantum number is changed, but valence electrons are same. So this type of representation, when you will do for AlBr3, it will be actually same. There will be no change. But if we want to answer this question, what will be the number of electrons present surrounding it? It is a total 6 electrons present surrounding aluminum. In this case also it is 6. If you consider the electrons from chlorine, total electrons surrounding aluminum is 6. So whether it is chlorine, bromine, fluorine, iodine, it will always be 6. It doesn't matter because you have replaced chlorine with the same group element. Bromine and chlorine are from same group. Their valence electrons are same. So it doesn't matter when you have changed. It will remain same. Okay. So that is the answer for the second question. Next we have structure, 4 different structures given for which molecule? Carbon monoxide. Remember, carbon dioxide is oxide of carbon. Another oxide of carbon is also possible, which is CNO. Only one oxygen. Correct Lewis structure for CO. Now how we'll do it? First thing that you have to do individually for carbon and oxygen, what is the number of valence electrons? For carbon, valence electron 4 because it is from group 14. Oxygen is group 16, number of valence electrons 6. So total number of electrons 10. Now if you simply count the electrons, total number of electrons, it cannot be more than 10 or lesser than 10. It has to be so. Now if you look at these electrons, the first structure total 6. So this type of structure means total 3 bonds are present and 1 non-bonding electron. But total number of electrons 8. It is not possible. Here also total number of electrons 8. Not possible. 8. Not possible. This is 10. Okay. So simply by counting the electrons, you can easily find out that the first structure, Lewis structure, is not possible at all. So this is very simple. You just have to count the valence electron for these 2 elements, carbon and oxygen, and you got your answer. A new topic, ionic bond or electrovalent bond. We already have some idea about the covalent bond, where there is proper sharing of electron between 2 atoms. Okay, but now you will see something different. And when it is possible, covalent bond is possible mainly you will see between 2 elements, both are non-metals. For example, F2, diatomic molecule, oxygen, chlorine, like this. Similar type of that is same atom. So all these 3 examples that I have given right now, F2, O2, Cl2, all are same atoms. It may be different atoms also. Just take the example of the previous problem, CO. So CO, carbon, oxygen, both are, oxygen is non-metal, carbon is slightly lesser non-metallic than oxygen, but still it is non-metal. Obviously it is not metal, and both are non-metallic type, and that is the reason here also it is covalent bond. There is sharing of electrons. But now we will see it is not sharing of electrons, so it is ionic bond or electrovalent bond. And when it arises when there is electronegativity difference between the 2 elements involved in bonding. That means one of the element will be metallic in nature, probably in the left hand side of the periodic table, group 1 or 2, but not necessary because there are still, you can get some metals in the P block also. But mostly the examples you will see preliminary or simple examples, mostly it will involve group 1 metal or group 2 metal. So when there is electronegativity difference present between the 2 combining atoms, this difference is high, large, then the least electronegative atom, least electronegative means which is more electropositive, it will completely transfer 1 or more depending on how many valence electrons it is having. It will transfer to the other atom which is more electronegative than this other combining atom. And what is the purpose of doing this? What is the motto they want to achieve? Their motto is to achieve nearest noble gas configuration, that is inert gas configuration. That is the purpose, okay? Because inert gas configuration is stable configuration. So that is why one is giving electron, another one is accepting electron, and once they have completed this process, they will achieve next inert gas configuration or previous inert gas configuration. Fine. Now, obviously, as the more electropositive atoms, it has donated electrons, it will be converted to cation, it will carry some positive charge, and the non-metal other member, it has accepted electron, there is excess electron, it will be converted to anion. So there is a positive charge, it may be +2, +3, whatever, but it is positive, and there is a negative charge. So these two different charges are present, and there will be some electrostatic interaction between these two, and this interaction is actually the bond. Okay, so you have to imagine it in a different way. In covalent bond, you have seen we draw some dot electron in dot style, and then we say it is a bond like this, A dot B. But here it is different. It is having A plus, B negative, and there is some interaction. So this is ionic, this is covalent. Okay, we have taken example of potassium and chlorine. These two atoms are present here, they have ionic bond between them. Now potassium, if you see, consider its electronic configuration, then after argon it is basically 4s1. So the previous noble gas is argon. Argon atomic number is 18 and potassium atomic number is 19. So one extra electron is present here. For chlorine, it is 17 is the configuration. So after neon is having atomic number 10. So 7 electrons you have to place. It is 3s2, 3p5. Now potassium is donating its single valence electron to chlorine. Why it is doing so? Because when it is doing so, it is converted to K plus, and K plus is basically the configuration of argon, that is K plus, and Cl minus. So one more electron is coming from K. So that is why now it has total number of electrons 3p6. So it has achieved the configuration of argon. So chlorine, previously atomic number is 17, now it is converted to 18, and potassium atomic number is 19. Now as it has lost electron, this is also 18. So both have reached this type of configuration, and that is the purpose of this donation of electron or acceptance of electron. Fine. So if we want to give definition, ionic or electrovalent bond forms when valence electron or electrons, in this case it is single electron but not necessary, valence electron or electrons of one atom is or are transferred permanently to another atom. So in this case potassium transferred its single valence electron to chlorine permanently, and ionic bond is formed between K plus and Cl minus. This type of bond is preferred between elements with comparatively low ionization enthalpy. Remember ionization enthalpy, we have learned about this in periodic table unit. So ionization enthalpy is applicable in this case for which element? It is for potassium, because potassium is donating electron. And what is the definition of ionization enthalpy? The energy required to remove the most loosely held electron. So this is the electron which we are removing. So ionization energy we have to apply for potassium. Okay, and comparatively low ionization energy. That means if ionization energy is very low, ionic bond formation will be facile. It can easily, you don't have to apply much energy. And the other one, as it is accepting electron means electron gain enthalpy. That is a reverse process of ionization energy or enthalpy. There you are removing electron, in this case you are adding electron. Okay. Sorry. So if the other one which is accepting electron is having highly negative value of electron gain enthalpy, obviously it will be better. That is why for chlorine we know it has very highly negative value of electron gain enthalpy. So this type of bond is preferred between elements where the element which is donating electron, it should have low ionization enthalpy. Should have, I mean to say, if it is having low ionization enthalpy, it is obviously better. And the other one which is accepting electron, if it is having very high, sorry, other element, if it is having very high negative value of electron gain enthalpy, it is better. Next we will see some more information for this bond. Any compounds in the crystalline state, there is ordered arrangement of, that is three-dimensional arrangement of these cations and anions, because in the previous slide we have seen there is formation of cation and anion. K plus is the cation, Cl minus is the anion. So these cations and anions, there is a ordered arrangement. It is not that the arrangement is very random. There is ordered arrangement, and this type of ordered arrangement is basically crystal. It forms some crystal, so they are in crystalline state. Now these compounds, they can crystalline in different format, okay, different crystal structures possible. Now details of these different crystal structure, that is obviously part of another unit which is in class 12, that is a solid state. Okay, so you can see all these blue circles, they are potassium ion, and black ones, they are chloride ion. So there is ordered arrangement. The cation first, then the anion, then again cation, and the sequence is going on. Now the energy required for the formation of 1 mole of potassium ion. 1 mole means Avogadro number of K plus. We always say in terms of 1 mole because the values of ionization energy or in electron gain enthalpy that are available in the database, that is always in terms of per mole. So when you are producing Avogadro number of potassium plus ion from Avogadro number of neutral potassium, you have to apply this amount of energy, which is 418.81 kilojoule. So this is the ionization energy you have to it is required for formation of 1 mole of K plus. Similarly, for Cl minus, it is electron gain enthalpy. So energy released during the formation of 1 mole of Cl minus. This is the value. There is a negative sign. We know electron gain enthalpy, it is mostly negative. Now, these are the values. If you add these two values, because this energy you have to supply. If you want to make 1 mole of KCl, you have to you need these two energy. So if you add these two energy, we'll get something positive value, because 418 it is positive and then minus 348 is negative. So sum of these two energies are basically 70.25 kilojoule, and this is one information. Another information is when you are making 1 mole of KCl crystal, starting from its constituent ion means K plus and Cl minus, then 718 kilojoule amount of energy is released. That means the energy that is present here and the energy that is released here, it is obviously different, and this value is much high. And why we are discussing this, it is basically related to Born-Haber cycle, how this 70.25 kilojoule energy is related to this 718 kilojoule energy. We'll also see that, probably not in today's class, in next class, in Born-Haber cycle. So these values are important. A qualitative measure of the stability of ionic compound. How you will know that the ionic compound that you have, in this case it is potassium chloride, whether it is stable or not? It is provided by its enthalpy of lattice formation or energy of lattice formation. Okay, that means when you are forming this lattice, starting from 1 mole K plus, 1 mole Cl minus, and you are making 1 mole potassium chloride ionic compound, then whether it will be stable or not, that you will be able to know from its enthalpy of lattice formation value. So in this case, it is 718 kilojoule energy. And not simply by achieving octet of electrons around the ionic species in gaseous state. So it is true that after donating this electron, now potassium is achieving noble gas configuration. That means its octet is complete. Now it has reached argon configuration. So outermost configuration is NH2NP6, like inert gas. Octet is complete. NH2NP6 means total 8 electrons. For chlorine also it is inert gas. Octet is complete. So individually it is true for both cation and anion, octet is achieved. But simply octet achieved is not enough. Maybe you can take any cation or any anion, and you can also make different types of pair, like you can make different types of ionic compound, and you can say that octet is complete, so it is stable. But no, that is not necessary. How you will know whether it is stable or not? So it is not mere achieving the octet of electrons, but we should also know what is the value of enthalpy of lattice formation. That value will actually give you, which is experimental obviously, whether the lattice is stable or not. So that we'll see in the next class. Today we are at the end of the session. Thank you for listening.